This video will cover section 4.1 on exponential functions. The definition of an exponential function with base b is f of x equals b to the power of x, where b is greater than 0 and not equal to 1, and x can be any real number. So in this section, we're going to talk about functions of this form. You should notice that this looks similar to a polynomial expression. The main difference here is that in a polynomial, the base value is the variable and the exponent is a constant. For example, x to the second power. Here, the base will be a number and the exponent will be your variable. So for example, 2 to the x, or 3 to the x, or 7 to the x. All right, so it's still going to involve exponents, but the behavior of the graph will be different because the variable is in a different location. Notice it says x can be any real number. So that's telling us that the domain of all exponential functions is negative infinity to positive infinity. So main focus of this section is on how to graph an exponential function. So we're going to just do the first one by just plotting points and using a table to kind of see a basic shape. And then in general, we're going to apply our transformation rules from section 2.5. So our example we're going to use here is f of x equals 3 to the x. So if I don't really have any idea what's going to happen and I'm trying to get a table of values that I can plot, we're going to set up a chart, x, and then our function f of x equals 3 to the x. Remember, the domain is all real, so I just chose my own set of x values to use. A couple negative numbers, -2 and -1, 0, and then +1 and +2. So if I plug -2 into my function, we would need to evaluate 3 to the power -2. All right, so you can do that on your calculator, just 3 to the power -2 and get the decimal. Exponent rules, however, tell us that when the power is negative, it means you can move the base to the denominator to make it positive. So 3 to the -2 is the same as 1 over 3 to the +2. And then 3 to the +2 power means 3 squared, or 9. So 1 over 9 should be the exact value for that. If I plug -1 in, 3 to the -1st means 1 over 3 to the 1st, or 1/3. So your calculator should show you 0.33333, etc. 3 to the 0, by definition, any number, any non-zero base raised to the 0 power always equals 1. 3 to the 1st would be 3, and then 3 to the 2nd would be 9. So if I plot those 5 points on a graph, at -2, we're at 1/9, which the decimal is like 0.1111, so barely above the x-axis. At -1, we're at 1/3, a little bit higher. At 0, we're here at 1. I labeled that 0, 1 because that's always going to be a point no matter what the base is, right? Any number to the power of 0 has to be 1. 1, 3, so over 1, up 3. This other point I labeled in general would always be the ordered pair 1 and then whatever b is, right? The b right here to the first power is always just b. So when that base changes, this is the general form of the second point we're going to use when we do our transformations. And then 2, 9 would be way up here. So we kind of see this general shape of a graph flow through those 3 points, or those 5 points. Notice here, as I move left, right, I could pick -3, -2, -3, -4, -5, etc. No matter what I choose here as an exponent, it can be -100. It's not going to result in a negative answer. 3 to the -100th means 1 over 3 to the 100th power. So that is still a positive number. It's just getting extremely small and very close to the x-axis. So notice I've drawn this dotted line here because the further left I go, the closer my numbers get to 0, but they never actually reach it. So exponential functions have a horizontal asymptote, and if it's just the base raised to the power x, that horizontal asymptote is going to be the the line y equals 0, or the x-axis. This line will move when we apply transformations, and it's going to move with any vertical shift. So when I have to shift my graph up or down, that's going to affect the location of that asymptote. It's going to move up or down the same number of units. As I move the other direction and let x get large, the exponent being a 2, and then if it was a 3, it'd be 27, and 3 to the 4th, it'd be 81. So this side is going to skyrocket very quickly toward infinity. Okay, so in this case, my horizontal asymptote only is predicting end behavior in one direction, not both directions. So we're going to use this kind of as our general shape to start with for an exponential graph. However, just remember that the base will affect the exact location of some of these points. This is the only point that would be common to every single original graph, 0, 1. All right, so our transformations from section 2.5, we are only going to worry about identifying vertical and horizontal shifts and reflections. We're not going to do stretches and shrinks. All right, so if our exponential function is the general form b to the x, if I add a number, it's going to shift the graph up that many spaces. And if I have the b to the x format and I subtract a number, it's going to shift it down. So just like before, adding or subtracting behind the function is going to move it up or down. That's a vertical shift. Horizontal shifts will be identified by a number being added or subtracted inside the exponent. Typically, a horizontal shift is identified by the adding or subtracting inside the function. In an exponential function, that's identified as being added or subtracted to the power. So in the exponent, if you add c, that's going to shift left c units. And in the exponent, if you subtract c, you're shifting to the right c units. So that's the horizontal shift. Remember, it's always backwards of the sign. And then reflections work the same way. A negative multiplied in front reflects it across the x-axis, and a negative multiplied on the inside or inside the exponent is going to reflect the graph across the y-axis. All right, so we're going to do a few examples of using transformations to graph. Just a quick note here, in the homework in my math lab, you are not going to be sketching the graph of the original. I just put it on here so we can follow along as to why the graph ends up where it is. You will just have to graph the final result and the asymptote. Don't forget about the asymptote. That will have to be sketched in, and these are not multiple choice for the most part. You're going to be doing these yourself, so you can't forget to sketch the asymptote as a dotted line. So g of x equals 2 to the power x plus 2. So this would be based on the basic shape of just 2 to the x. The transformation, since I'm adding inside the exponent, is going to move my graph left 2. And since there is not a vertical shift, the horizontal asymptote is going to stay at y equals 0. So I would start over here by graphing the 2 to the x. So the 0, 1, and the point 1, 2, remember the 1b, b being the base 2, would be kind of the general starting point. That's the 2 to the x. So if I take those 2 points and shift everything left 2, this point moves left 2 and lands here. And then this point would move left 2 and land here. So I would then sketch in my final answer right here. Same shape, just shifted left 2, and then my horizontal asymptote at y equals 0 would stay where it is. In my math lab, you will be asked to, I would probably just go ahead and plot your 0, 1, and then you'll have to fill in the blanks for whatever transformations are going to be applied. So there's a little slider where you can slide the graph left or right or up or down for the horizontal or vertical shifts. There's a box to click if there's any reflections, etc. And then there's a box where you can type in what your base is. Okay, you just have to fill in those blanks and it sketches for you. You'll have to click on the tool that shows the exponential shape, and then it will do the rest. Then there's a separate tool to graph a line. So when you sketch in your asymptote, you'll have to click the line tool, click the dotted option, and then put in your line. All right, the domain is all real numbers, always on an exponential, and the range will depend on whether the graph is above or below the asymptote. So since it lands above the y equals 0, my range is 0 to infinity. Never included here. There's always a parenthesis on the endpoint for the range. Okay, here's another example. G of x equals 4 to the x minus 1. So this graph will be based on the basic shape of 4 to the x, and this time we're subtracting 1 behind it, so that's going to shift everything down 1. And since that is a vertical shift, that's also going to move the horizontal asymptote down 1, so it's going to land at y equals negative 1. So my original would be at the point 0, 1, and then 1, 4. So this dotted curve right here would be the original starting point. If I shift it down 1, this point moves down 1 to here, and then this point moves down 1 to here. So my new graph is that original shifted down 1, and my horizontal asymptote down here is sketched in at y equals negative 1. Domain again is all real numbers, and the range is above the asymptote, so parenthesis negative 1 to infinity. This example has a reflection involved, and it also has a vertical shift. So there's two transformations here. So g of x equals 3 to the power negative x plus 2. So my basic shape that I will start with will be 3 to the x. There's a transformation. There's a negative multiplied in front of x inside the exponent, so that's going to cause a reflection in the y-axis. And then the plus 2 behind it is going to shift it up 2. So because there's a vertical shift and we move up 2, my horizontal asymptote is going to end up at y equals 2. All right, so my original graph, 0, 1, and 1, 3, is this curve right here. So if I have to reflect that in the y-axis and flip it across, notice this second curve, this dotted line, or this dotted curve here is just showing the reflection in the y-axis. But I'm not done yet, so that's why I still made it a dotted line, or a dotted curve. And then we're going to move it up 2 from there, so this point goes up 2, and then this point that ended up over here moved up 2. So that's how I get this result. And then my y equals 2 lands right here. Don't forget to put that in your graph. And then you're done. So in my math lab, you would be sketching your asymptote wherever it ends up based on your vertical shift. You would click on the exponential shape from the tools. And I think you plot your 0, 1, and then there's a box that'll pop up, and then you can click your reflect in the y-axis and move up 2, and it will do the rest. All right, the domain is all reals, and this graph lands above this line, so the range would be then parenthesis 2, comma, infinity. All right, a lot of exponential functions behave according to a model that involves what we call the natural base, and it's indicated with the number e. So it's kind of like pi. It's a number, but we give it a special name because it has a lot of real applications. We're going to see one here in a minute at the end of this section. So the number e is approximately equal to 2.71828, etc. Okay, and there's a key on your calculator if you ever need to utilize that number, which you will fairly frequently here as we move forward into chapter 4. So on the TI-84, E can be found, there's two places, but the most common place is if you hit your second button, the blue second button, and then down further along that left side of your keyboard, there's a key that has the letters LN on it. So if you notice in blue, right above your LN key, there's an e to the x. So if you hit second to access the blue function, and then the LN, E, and then a power will pop up for the exponent, and you can type in whatever exponent you need. So if you needed to evaluate, say, e to the negative second power, you would hit second ln, and this would come up on your screen, and then inside of the box, you would type in the negative 2, using the negative in the parentheses at the bottom of your keyboard. So typing in negative 2 and pressing enter should give you this result. All right, so let's look at an example of graphing a rational function that involves the base e. g of x equals negative e to the power x minus 1 plus 3. So here our basic shape would be the graph of e to the x, which looks the same as the others, 2 to the x, 3 to the x, 4 to the x. It's just that that base is that 2.7 approximation. All right, that graph is going to get moved minus 1 on the inside. It's going to shift it to the right 1. The negative in front this time is going to reflect it in the x-axis, and then the plus 3 behind it is going to move everything up 3. So because we're moving up 3, we're going to have a horizontal asymptote at y equals 3. So on my graph, I would start with my e to the x, so that's again 0, 1, and then it's this shape of a graph, just like the others were. We would be moving to the right 1, so that point would move over 1. Then it would reflect across the x-axis and move down here, flip upside down, and then it would move up 3, 1, 2, 3, and land right here. And because it flipped upside down, right, my shape is now upside down of the original. And then my y equals 3 up here is my horizontal asymptote, and then my graph fills in below it. So the domain again is all real numbers, and this time because it got reflected across the x-axis, notice the range is going to be negative infinity up to 3 because my entire graph is below the the horizontal asymptote. All right, most of the section are the graphs. The end of the section, there's a couple problems on applications of exponential functions, and in particular, compound interest formulas. All right, so there are 2 formulas that we can use to calculate compound interest depending on what we are given. All right, so the rules for using these formulas in terms of defining what the variables mean. After t years, the balance A in an account with principal P, principal means how much you start with, an annual interest rate R, that interest rate should always be in decimal form, is given by, and it depends on the other information as in terms of which formula you're going to use. For n compoundings per year, so if it says compound monthly or compound daily or compound semi-annually or compound quarterly, there's a word there to indicate a certain number of times. The formula is A equals P times the quantity 1 plus R is the interest rate divided by N, that's the number of compoundings, all of that raised to the power of N times T, T being the number of years. If it says you're going to compound continuously, continuous compounding, the formula is different. It's A equals P, the principal, times that number we talked about a minute ago, E, so you'll use your calculator for that part, and then the exponent of E is the interest rate again in decimal form times the number of years. So RT is the power. So we're going to try an example that utilizes both formulas. It says find the accumulated value, that means A, of an investment of $5,000 for 10 years at an interest rate of 6.5%, compounded, semi-annually, quarterly, monthly, and continuously. So we're calculating 4 different numbers here. All right, so the word semi-annually means that the n value is 2. That means 2 times a year. The word quarterly means the n value is 4 times a year. Monthly would mean 12 times a year. And then part D is continuously, so that one we're just going to utilize the other formula when we get to part D. All right, so it says that we were depositing $5,000, so that means that the principal is $5,000 for 10 years, so T is 10. The interest rate was 6.5%, and we're always supposed to use a decimal form of that, so 6.5% in decimal form is 0.065. You're just going to divide 6.5 by 100 to get the decimal. And then we're ready to plug things in. So for part A, we said that semi-annually meant N was 2. So A equals P 5,000, parentheses, 1 plus R 0.065 divided by N, again, that's the 2, close parentheses, raised to the power of N, the 2, times T, which was 10. So if you have a graphing calculator, again, it's very easy to evaluate these formulas because you can just type it all in at once on your screen. You don't have to do the inside part first and then the power and then the 5,000. So you can just type 5,000 parentheses 1 plus 0.065 divided by 2, just hit the division key, close the parentheses, and then your exponent is right here, the caret, power, and then in the power, 2 times 10. If your calculator is an older version and it doesn't give you the little box for the exponent, make sure that the 2 times 10 is enclosed inside of a parentheses to make sure they're getting multiplied in the exponent. Or you could just type 20 if you can do that in your head. So if you just enter that on your screen and press enter, it just gives you the answer, right? There's no extra steps. You will be expected to round appropriately to the nearest cent. So $9,479, and this would round to 19 cents. Okay, be careful if you are not typing it all in at once like this and you're doing it in parts, like if you're going to do the division part first and then add the 1 and then do the power, do not round off any intermediate answers. Because if you do that, you could get the wrong number of cents because this will end up being skewed a little bit with your decimals. So it's best just to type it all in at once, press enter, and write it down. All right, so if I move on to part B, for N equals 4, A equals, again, P is still 5,000, 1 plus interest rate, 0.065, we just change our N value to 4. And then in the exponent, this is N times T, so we're changing that N value to 4. And then press enter on that one, gives you $9,527.79. When N is 12, again, all this stays the same except for the N, which is down here on the bottom, and up here in the exponent, that changes to being a 12. You get $9,560.92. Notice that the amount is going up slightly, right? Not a lot, but a little bit every time you increase the number of compoundings. And then finally on part D, when it said compound continuously, that's when we have to switch formulas. So it's the principal, which was still 5,000, E, so you would type in here, I don't have it shown here, but you would just type 5,000, and then second function, and then your ln would pull up the e to the power, and then in the parentheses, or in the box, you would just type 0.065 times 10 and close the parentheses or arrow out of the box. And when you press enter on that one, you get $9,577.70. All right, so that is the end of section 4.1.